Hi there, this is Mike Lopez at UniCourse.org, and in this video we should be looking at the mysterious root 3 and 3-phase networks. Quick look here, we can see we have some phase voltages in brown, black and grey, and these are the IEC 60446 standards which the UK has now adopted. We'll be checking out the RMS and peak values of these phase voltages, and we'll also be looking at the line voltages which give these numbers here. 400 volts is familiar to you in a three-phase system, and the peak values, we'll see how we get those peak values and where on earth this mysterious root 3 comes from. We're then going to move on and have a look at a couple of phases in a three-phase UK system. Phase 1, Phase 2, and we'll see how we need to invert one of those phases as we've done here, and move on and analyze the system in terms of J notation, and step by step we will arrive at this mysterious root 3 figure. We'll then be moving on to using the TINA simulator. Now you can download an evaluation or a student version of that simulator, and in particular this analysis we'll be looking at star generators, and here we have a star load, here we have star generator, and here we have a delta load, and we'll be examining the phase voltages and line voltages in each of those systems. And finally we'll be looking at the microcap simulator, and you can download a student or evaluation version from the internet. And here in this simulator we've drawn a star delta arrangement, as you can see here, and what we'd like to do is run a transient analysis and be able to pick out those line voltages, as you can see from these peaks here, are quite high, and also the individual load current waveforms which we show here. Okay, so let's get on and start all this analysis. Okay, so let's have a look at the UK mains in terms of three-phase. We start with some blank axes. Up here on the vertical we have voltage, of course, and along here on the horizontal we have the time axis. Let's introduce our first sinusoid. Here we are. So this is what you receive in your house. This is 230 volts AC, 50 Hertz. Now when we say 230 volts, we mean this point here in terms of that level, which is called the RMS, root mean square level. Okay, so it's not the peak value. The peak value, as you can see, is a little bit higher than 230 volts. In fact, it's root 2, which is 1.414 times 230, which gives us a value of 325 volts peak at that level there. So each of these is 325 volts, and on the other side of the axis you have negative 325 volts at this point, and this point, etc. as we move along. Now let's introduce a second phase. Now you'll notice the first phase was brown, our second phase is 120 degrees difference from that one. There's black, and in the UK IEC 60446 the third phase is grey. Okay, so we have brown, black and grey, and each of these are 120 degrees apart. Okay, what then happens if I was to just turn off the grey phase and not clutter the diagram too much? If we're looking at, there's one phase voltage and there's another phase voltage. What is the difference between the two phase voltages? Well, that will give you a line voltage. So therefore, if we're going to find the difference between these two, what we actually need to do is to invert one and then add it to the first one. Okay, that will give you a difference. We're not just adding these two guys together, because at this point here, you know, that is maybe round about 150, 160 volts. If you added, you would expect a value to be about 300, 320, which is not what we're doing. What we're doing is we're finding a potential difference between these two voltages. Okay, so what we end up with is indeed this guy here. Okay, so this pink graph here shows you the line voltage. Now, yes, those levels are much higher. 325.3 up here, 230 volts here for our phase voltages. But what we then have is a line voltage which has got an RMS level of 400 volts, and I can draw that line in there, the pink line. Okay, so don't forget, in pink here we're talking about line voltages, and a corresponding peak for that line voltage drawn here in green is an amazing 563.4 volts. It's rounded up slightly, but 563.4. You know, this 400 was actually rounded up from 398 and a bit, but in the UK we just round it to 400 volts RMS. Okay, so what we can see then is that if you do some sums, you work out 230 volts and do something with that 230 to arrive at 400. What you in fact have done is multiply 230 by root 3, and that will give you roughly 400 volts. So our aim here is to do some sums and work out where this magical or mysterious root 3 comes from. Okay, so let's have a go at that. Okay, so the analysis in terms of finding out where root 3 comes from is pretty much given to you here. I've done that so that you don't have to watch me scribbling away and wasting time on the video. So let's start with this diagram over here. On the horizontal we have a single phase, our brown phase. Okay, rather than use 230 or 325, those figures, why don't we just use a nice standardized, normalized, if you like, 1. Okay, so we have a phasor of length or magnitude 1. Because it's on this horizontal, it's 0 degrees phase. Okay, so it makes 0 degrees with the horizontal axis, which is our reference axis along here. Okay, what we've also done is drawn in phase 2 in black, and we've normalized that, so that also has a magnitude of 1, and it lags, hence this minus sign, by 120 degrees. Okay, so that's standard two-phase analysis for the UK. What we'd like to do is to work out what is the difference between these two voltages. Okay, so that's what a line voltage is. A line voltage is a potential difference. Okay, and I underline the word difference because that's really important in being able to determine this root 3 figure down here. Okay, so a difference means phase 1 take away phase 2. Okay, so we're looking at somehow trying to invert phase 2. The maths must say P1 minus P2. So what we then say is, well, it's easy for us to add phases together. Okay, we just do P1 added to minus P2. So that means we need to invert P2 and add it to P1. Okay, so invert and add. That's what's done here in the maths. Okay, so you need to invert P2. Here's P2 sitting here. If you were to invert that, that means, you know, make it go 180 degrees round the circle again, so it's actually going to feature over here. And that's what we see in this diagram here. Okay, so that's been drawn there. The brown phase has stayed the same, we haven't touched that at all. The P2 phase has been inverted, okay, hence this minus sign here. And then if you look at the diagram, you'll see there's 60 degrees between these two phases, which is important for our analysis. Okay, so we need to then turn to J notation. And J notation, essentially, we have the real values along the horizontal, and we have the J terms along the vertical. So we can analyze phase 1, and we can say phase 1 has 1, or a magnitude of 1, in the real direction. Okay, and indeed it does. Here it is. It's got a magnitude of 1. In terms of j, it's 0. So there is no j component for this. You know, it's along the horizontal. There's no plus or minus figure in the j axes at all. Okay, so we could just write this as j0 is just nothing, so we can just write p1 equals 1. So it's wholly real phasor. If we then look at minus p2, we'd like to add minus p2, remember? Add minus p2 to p1. So minus p2 is over here, and what is the real component? Well, you use a little bit of trigonometry. The real component is 1 times the cos of 60, and the vertical component, or the j component if you like, is going to be 1 sine 60. So we need to work out what these things are. So 1 times the cos of 60 on your calculator, you just basically write cos 60, and it will give you 0.5. Okay. If you then work out what the sine of 60 is, the sine of 60 comes to be 0.866. So we can wholly describe minus p2 by 0.5 plus j 0.866. So 0.5 here, this bit along the real axis, and we're in plus j, so we're going to be that direction there, okay, that distance. We're looking at 0.866 length. Right. And as you know, if you want to join these two things together, so we're going to be 1 added to 0.5 added to j.866, so basically we arrive at the 1 and the 0.5 give you 1.5, and the j bit is just on its own, so it's just plus j.866. If we were to determine the magnitude of the resultant from these two, okay, so actually undertaking the phasor addition of these two, so you draw a line along there, you draw a line along there, you form a parallelogram, and the phasor goes from this point all the way across to around about here. You use a little bit of Pythagoras, and you need to get the square root of the sum of the squares. The square root of 1.5 squared plus the square root of 0.866 squared. Okay, so the 1.5 squared gives you 2.25, and 0.866 squared gives you 0.75. Try it on your calculator. So we actually end up with root 3. Okay, so there's root 3 demystified for you. Let's now turn to that TINA simulator and draw ourselves a couple of three-phase systems. This top system here, okay, we have a star-star arrangement, and along the bottom here we have a star-delta arrangement. And you'll notice that I've put some digital and analog meters in here to measure phase and line voltages. Okay, so let me click on the AC simulation, and immediately we have 230 volts, and don't forget this is going from ground, or you can use neutral if you want to stick with neutral and change it to ground, that point there, from there to there. So we're looking at the voltage across this particular phase generator here. It's giving us, digital meter at least, is giving us 230 volts, so we infer from that the digital meter actually gives us, at the moment, RMS measurements. Okay, what you'll notice here is that the analog meter is actually giving you a peak value, and we mentioned earlier 325 and a bit volts peak. Okay, that's the phase voltage. Now this meter is arranged from line to line, so this is giving us line voltage. Okay, that's saying a RMS line voltage of 398.4, and in our earlier diagram we rounded that up of course to 400 volts, and the analog meter is giving us 563.4, which is pretty much that peak value for the line voltage that we also analysed earlier. Okay, we look down here to the star delta arrangement. Again, we can see 230 volts for the phase voltage and round about 400 volts for the line voltage. Okay, now let's see if we can bring in an oscilloscope to this arrangement and have a look at the waveforms. Okay, I have the oscilloscope set up in the TINA simulator. To do that, I needed to insert some outputs, as they're known. Okay, so tell the oscilloscope where to make measurements. So VP output I've placed from this point to this point. VP is V phase, of course, and VL or V line goes from that point to that point. Okay, so between two lines. And I've set up the oscilloscope time base 2 milliseconds per division, so from there to there is 2 milliseconds, and 200 volts per division vertically, so from there to there is 200 volts. Okay, if I now run the simulator and I'm looking just at the phase voltage at the moment, there it is, moving along nice and slowly. If I just stop this at a convenient point, let me just let it run for a while and then hit stop. Okay, what I'd like to do now is to turn on cursor mode, so I'll get cursor A, which is in red, and move along to the peak over here. What you see is Y, or the vertical, for cursor A, 325 volt peak. Now that is the peak value we determined for a phase voltage. Okay, let me just erase that trace, move along to turn off the phase voltage and turn on the line voltage, which we are. Hit run, and what we can see here on the line voltage is that looks a bit bigger than what we had for the phase voltage. Let's hit stop, let's grab that cursor, move over to the peak for the line voltage, and you can see another familiar figure here, 563 and a bit volts for the peak line voltage. Okay, and then you can divide that by √2 and you should get around about 400 volts RMS for the line voltage. Okay, moving on to the microcap simulator, we have here in the grey dashed box a star generator. Okay, and we're denoting the peak values for each of the voltages that's necessary for these voltage generators. So 325.3 peak, as you now know, is the same as 230 volts RMS, and we plump for some values over here in the load, all identical as you can see. So each load is 20 ohms and 200 millihenries in series, and the idea is, let's see if we can determine graphically what these currents might be through each of these loads. Okay, and to do that, what we can do is run ourselves a transient analysis. So analysis, transient. Okay, we're moving along to the transient analysis limits dialog box, and I've got some voltage differences here. Voltage phase 1 take away the voltage at phase 2. I've got the voltage phase 2 minus the voltage at phase 3, and we've got the phase 1 voltage take away phase 3 voltage. Remember earlier we were looking at taking away or subtracting phase voltages. That gives you a potential difference, okay, which is what voltage is all about. And we've also asking here for the currents through R1, R2 and R3, and I've set the X and Y ranges, as you can see, to auto always, which is always very convenient. Right, let's do a run on this. This might take a few seconds before the plots appear. Okay, waiting patiently. Let's see what comes out. Hopefully soon they're going to appear. Here they are. Okay, we have up here some line voltages. Okay, and if you want to determine what these values are, let me have a look and go for cursor mode. Click on cursor mode. That enables me to put in some markers up here, Okay, so this marker is saying 1.003 seconds. We have 563.418. In other words, 563.4 volts peak on the line voltage, which again is something we're now familiar with. Okay, if I move down here and look at these currents and bring this marker over, need to go to a peak somewhere. Okay, we have a peak current of 8.544 amps. Okay, if you were to go away and work out what XL was, XL is 2 pi FL, okay, for each of those loads. So 2 pi times 50 times the inductor value 0.2, okay, you end up with 20 pi, and 20 pi comes to 62.8. If you then divide this peak voltage value here, okay, 563.4 almost, divide that by what the overall impedance would be, and the overall impedance is the square root of 20 squared plus XL squared. XL comes out to be 62.8, so impedance for that series combination of R and L is 65.9 ohms. So 563 divided by 65.9 should give us 8.55 amps for the current. Let's go back to the current and check that out. Go to any one of the peaks. There we go. Nearest damn it, 8.55 amps. Okay, and that's pretty much the essentials of transient analysis and using markers in microcap. Okay, thank you. This has been Mike Lopez. Thanks for watching, and see you next time.